Is my PPT audible? Somebody can respond.
Yes, sir.
Okay, thank you. Thank you. Yeah, I think syllabus I'm not going to discuss. I would like to give some brief information about the powertronic converters, powertronic system, solid state switches, and then we learn today only one experiment. That is the static characteristics of MOSFET and IGBT. Only one experiment we are going to learn comfortably cool. Okay. Any doubts? Definitely you can unmute and talk to me at any time. Now, if you say the power electronic system, the powertronic system has got power processor or powertronic converter or some load. Load can be static load or dynamic load. When you say static load, maybe my lamp appliances, refrigerator, which are static in nature. When you talk about dynamic load, some induction motors, industrial drives, AC drives, DC drives, they are the dynamic load. Some motion will be there. And controller. Controller can be a microcontroller or a digital signal processing or a FPGA or very conventional analog electronic converter or digital electronic converter. Any kind the controller can be. Then these are the three important blocks for your power electronic system. When I say system, a ample of events are the devices which are similar in nature. They gather to make a one particular system. I require a power electronic converter. I require a controller. I require a load. Some closed loop mechanism here. Maybe reference signal will be given by the user. What the user may request. The reference signal may be a temperature, voltage, current, speed, velocity, whatever the reference input user can give. So that is taken as input by the controller, and it's going to control the output power of the power processor. So power input and power output. Generally power input can be AC or DC, power output can be AC or DC. So we have 2 to the power of 2, 4 combinations will be there. So these are the combinations we have. DC to DC converters, choppers, we say. AC to DC converters, rectifiers, and DC to AC converters, inverters, AC to AC converters, AC voltage controllers, or cyclo converters to vary the frequency also. So these are the very, very basic 4 types of the converters. Input can be DC or AC, output can be DC or AC. Then what are the components of this polytronic converter? There are 3 categories are there. First category is semiconductor switches or a solid state switches. Under that there are 3 family members. We can have a diode family members, maybe a conventional diode, a power diode, varactor, some different type of diodes will be there. Schottky diode. Then transistor family member, very 3 important transistor family members. We have BJT, bipolar junction transistor, MOSFET, metal oxide semiconductor field effect transistor, IGBT, insulated gate bipolar transistor. These are the family members of transistor. So how you compare diode with the transistor? Diode has got 2 layers, 1 junction. Transistor, 3 layers, 2 junction. The next advancement is thyristor family members. So thyristor is very vast. It can handle more power, more voltage, more current. It can be used in the HVDC, HVAC systems, high voltage DC, 400 kV systems and all. So thyristor is basically 4 layers, 3 junction device. 4 layer, 3 junction is. So every time if you observe, 1 layer is adding up, 1 junction is adding up. Then which are the thyristor family members? The very first member is SCR, silicon control rectifier. Then we have a triode that work on AC, diode that work on AC. Then we have a RCT, reverse conducting thyristors, MCT, mass conducting thyristors. So many family members are there in the thyristor. And even G2O, gate turn-off thyristors. So we use these semiconductor switches or solid state switches in the polytronic converters. Then energy storage elements. So inductor capacitors plays a vital role. Very important thing is in every polytronic converter, we ensure that inductor has to energize, it has to de-energize. It has to energize means it is the highest value of the energy, it has to de-energize. So inductor is a basically current element. Inductor is a current element. Then when you have a huge coil, it will work like a current source. It can generate a constant current for some period. And even if you take armature of the motor, it's a dynamic load. The armature of the motor is the inductor which has got a energy storing property. It stores the energy and give the constant current. I can replace the motor with a current source element. So normally somebody asks what are the current source element? Nothing but my coils which can store the energy. Then capacitors. When you see the capacitors, basically these are the voltage elements. voltage elements. So which work like a voltage source, something like a battery. We have a, what we called fast capacitors, super fast capacitors, which we use in the EV technology and all. So this is the capacitors, inductors plays a vital role here. Even capacitor should charge, discharge, charge, discharge. You cannot pump the energy to the capacitor continuously. It will buy, it will burn. Even inductor, you have to energize, de-energize. Don't tell inductor charging, discharging. Inductor, you have to tell the word energizes, de-energizes, capacitor charges, discharges. And we say capacitor voltage element. Why we say voltage element? It absorbs all the ripple content in the voltage. Inductor absorb all the ripple content in the current. Inductor absorb the ripple content in the current. Capacitor absorb the ripple content in the voltage. Apart from that, we have other components, transformers, control circuits. This put together, we have a powertronic system. Then one should know about the solid state switches. Very importantly, what are the various categories of the solid state switches? The very first one is based on controllability. Based on controllability. Very first one is uncontrolled switches, power diode. Why it's called uncontrolled? I don't have any control terminal here. Anode and cathode will be there. The moment the voltage across the diode is more than the threshold voltage, cut-in voltage, it will turn on. Maybe 0.8 volt beyond the junction, whatever the junction capacitance effect or the depletion region. Beyond that it reaches, it will be turned on permanently. So I don't have any control here. So diode can be used as a one-way switch. It allows power flow in one direction. It blocks the power flow in other direction. So it's uncontrolled. Semi-controlled switches. Semi-controlled means I can control these switches only to turn on. I don't have the control to turn off. So when you talk about SCR or a triac, which are there in some experiments, silicon control rectifier. So if you handle DC voltage to the SCR, when you give the DC voltage to the SCR, it will immediately turn on. It will latches. It will lock. So if you want to turn off, either you have to switch off the supply, but we cannot switch off the supply under online conditions. You have to give the reverse voltage across SCR. Some mechanism you have to do such a way that to turn off the SCR. So, but when you handle the AC supply in the SCR, if you take up the 50-year supply, my sine wave goes 100 times 0. Sine wave goes 100 times 0 because 50-year supply, 50 cycles per second. So per second, 50 cycles will be there, 100 times it changes its polarity. So 100 times when it goes to 0, obviously SCR will be naturally turned off. So the basic condition is in the SCR there is something called latching current and holding current. So all those things we discuss later. Have a rough idea. So when the SCR anode current is more than latching current, it will turn on. When the SCR anode current is less than holding current level, it will turn off. So holding current will be very, very small. So this is some mechanism where SCRs will be used, but SCR can handle more power than your BJT or a MOSFET or IGBT. Even triac. Triac is nothing but two SCRs connected in anti-parallel. We connect two SCRs in anti-parallel. It has got a control terminal called gate terminal. Anode, cathode are the main terminals. Gate is the control terminal that is there in both SCR and the triac. When you go for a fully controlled switches, nothing but your transistor family members like BJT, MOSFET, IGBT, we can turn on, turn off whenever you want to do so. So when you give the base drive, BJT will be turned on. Stop giving base drive, it will be turned off permanently. But that is not the case in SCR. If you give the gate signal, it will turn on. If you remove the gate signal, it won't turn off. Because anode current will be continuously flowing, it will be latched. That's a problem in the SCR. Of course, we have some mechanism to overcome from that. GTO, gate turn off thyristor, one of the family member of thyristor, that has got the property to turn on and turn off. Even though it's a thyristor family member, GTO can be fully controlled. It can be fully turned on and fully turned off. One of the thyristor family member. So of late people use the GTO in the your BMRCL, some what you say industrial drives applications for to handle more power. Then, based on nature of control signal, what type of control signal you give, whether you give pulse or whether you give 5 volt. If you take SCR track and all, it's enough to give a small pulse. Maybe the width of the pulse will be some 50 microsecond or 100 microsecond. That's sufficient to turn on the SCR. Thereafter, pulse is not at all required for the gate terminal. But that is not the case in the BJT transistor. The transistor, as long as you give the 5 volt, it will be in on state. The moment you reduce the voltage, base voltage to 0, it will go to off state. That we say fully controlled. fully controlled. We say that is a fully controlled. One moment.
Sorry,
there are around 33.
announcement, sir.
ಹೇಳ ಎಷ್ಟು ಗಂಟೆ ಕ್ಲಾಸ್
3 o'clock. ನಿಮ್ದು ಎಷ್ಟು ಗಂಟೆ?
ನಾನು 2:30 ಸ್ಟಾರ್ಟ್ ಮಾಡಿದ್ದು ಬಿಕಾಸ್ ನಮ್ಮ ಮೀಟಿಂಗ್ ಇತ್ತು 3:30.
3:30 ಇಲ್ಲ ನಮ್ಗೆ ಹುಷಾರಿಲ್ಲ.
ಕ್ಲಾಸ್ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ ಮುಂಚೆ
ಎಕ್ಸ್ಟ್ರಾ ಕ್ಲಾಸ್
ಇನ್ನೂ ಅನೌನ್ಸ್ ಮಾಡಿಲ್ಲ.
ಹೇಳಿದ್ದೆ ಮೊನ್ನೆನೇ
ಈಗ ಅನೌನ್ಸ್ ಮಾಡಲ್ಲ ನಾನು.
ಹೇಳ್ಬಿಡಿ ನೀವು ಕಂಟಿನ್ಯೂ ಅಂತ ಹೇಳ್ಬಿಡಿ.
ನಾನು ಅದೇ 1 hour ಮಾಡ್ತೀನಿ ಅಷ್ಟೇ. Okay, students, 3:30 up to 3:30 have class. Thereafter, Priya ma'am's class she has announced already, but it won't be there because ma'am is busy with some official work, right? So mine is the last class for today's session. Okay? Yeah. Thank you. Okay. Yes. So these are very, very fundamentals one should know. I want to share this PPT to you, all of you. I put it in the group. Please go through it. Most of the Viva questions will be covered here. Then, level triggered or continuous control signal switches means all your transistor family members, as long as you give the base signal, base drive signal, as long as you give the gate drive signal to the MOSFET or IGBT, it will be in on state. The moment you make the base drive voltage 0, it will go to off state naturally. But that is not the case in SCR. If you give the pulse, it will on. If you remove the pulse, it will be still in the on state only. That what you call latched mode, latching mode. But if you take SCR, GTO, MCT, almost all the thyroid family members, you give only one small pulse, it will be on. I don't want to give the pulse further so that losses will be reduced in the control terminal loop. Control terminal loop losses will be reduced. That's the main advantage. Then, based on direction of conduction, in some situations, I expect my switches to conduct current in both the directions. Some situations, I don't want to conduct current in both the direction. Maybe one direction current flows, that's fantastic. Now, first one, unilateral. Unilateral means this switch is capable of conducting current in only one direction. Diode, one direction. SCR, BJT, IGBT, GTO, MCT. If you do not know the abbreviations, SCR, silicon control rectifier, BJT, bipolar junction transistor, IGBT, insulated gate bipolar transistor, GTO, gate turn off thyristor, MCT, mass control thyristor. All these switches conduct current in only one direction. It won't conduct current in both the directions. Rather, bilateral switches, you take a track. Track is a very common element used in the fan regulators, what you have at home, fan regulator. Right? In track, it can conduct current in both the directions. RCT, reverse conducting thyristors, diode that work on AC. So all these elements conduct current in both the directions. Then, based on voltage blocking capability, what do you mean voltage blocking capability? For example, you have a transistor. Between collector and emitter, you have connected 200 volt DC with a bulb, 200 volt bulb. So collector to emitter in that particular loop, I have a 200 volt DC and one bulb in series in that particular loop. Left hand side control terminal, you have the base and the emitter. To the base and emitter, I'm going to give a small voltage of 5 volt. The moment I give the 5 volt, the transistor will be turned on, so the bulb glows. Then, the moment I remove the base drive, the voltage drop across the transistor will be 200 volts when it is not conducting. When the switch is not conducting, the voltage drop across the switch will be nothing but the supply voltage of 200 volts. It has to handle 200 volts when you don't give the base drive. That is an open circuit, right? When the switch is open, obviously across collector and emitter terminal, the supply voltage will be available. It has to withstand. That we say forward blocking voltage. Forward blocking voltage is the voltage which the switch can handle when the gate signal is not given or the base signal is not given. So is it capable of handling that? Is the question. Yes. BJT, MOSFET, IGBT, all your transistor family members can handle this high voltage in one particular direction. Maybe collector positive, your emitter negative. It can handle one particular direction. But you give the reverse voltage, it will burn. That should not happen. So we have a next category called bipolar switches. We take SCR, GTO, tracker. All these switches can handle both positive voltage of 200 volts, negative voltage of 200 volts, it can handle without any problem. That's the main advantage of bipolar switches. Polar means, when I say polar means, it's nothing but voltage point of view. Unipolar, bipolar. Unipolar can handle voltage of one polarity. Bipolar can handle voltage of both the polarity. You reverse the voltage and give minus 200, it can handle. So those are the based on the voltage capabilities. Right. So this particular PPT slide is very important. One should understand what kind of switches we have. The first category means based on how you can control them, whether you can give the base, whether the gate terminal is there or not, whether the control terminal is there or not, whether you can turn on or whether you can turn on, turn off, both you can do or not is a question. Controllability. Second category, nature of control signal. What type of pulse you give to the switch to turn on. You want to give a small pulse sufficient to turn on forever, or you want to give a continuous pulse for it to turn on forever is a question. Third category, which direction current flows, either one direction or both the directions. Fourth category, voltage blocking capability, whether it can handle both positive voltage or negative voltage, reverse voltage. These are the switch categories. Now I would like to share some information where and all the power converters are used. Let us say UPS, uninterrupted power supply. This we say offline UPS, which means that mains one is a DESCOM power which is fed to the load through static bypass switch. So then when the power goes off, immediately the second portion will come to the picture, mains 2. Mains 1, mains 2 both are 230 only, common point. So under normal conditions, mains 2 what it will do, it will convert AC to DC and use for charging the battery. The battery will be charging continuously. Once the battery is fully charged, then the power is cut off there. Then once the power goes off, when the DESCOM power goes off, the power available in the battery, which is a DC voltage, is inverted to AC using inverter. Inverter converts DC voltage from the battery to AC. So I got an AC output. And using isolation transformer, we use isolation transformer for two applications. One is I want a perfect electrical isolation. Second thing is I want to step up the voltage also. If the inverter output is very small voltage, I want to step it up and then give to my load there. Two operations can be performed here. So this is a very common offline UPS. Offline means I'll be getting power, raw power from the DESCOM always. At the same time, the battery will be charging. Once the battery is fully charged, the mains 2 also will be turned off automatically. Once the main power goes off, whenever there is a blackout or the main power goes off or interruption, that time your battery will take over the load. Battery will drive the energy to the load through inverter. Okay, this is my UPS system. Here, what and all we can see here, we can see rectifier AC to DC, inverter DC to AC. So we got two power electronic system here. One is rectifier, one is inverter in my UPS. Then take a laptop. So in the laptop, we have the input is 230 volts. So maybe say I'm having a 100-watt laptop, 100-watt laptop. Now what the very first stage of the quadratic converter is that rectifier circuit. Here there's a PWM rectifier. This is not like a conventional rectifier. We put a diode rectifier, bridge rectifier, and then we convert to AC to pulsating DC, put a capacitor, put a regulator to get the DC voltage. Not that. PWM rectifier concept is altogether different that we discuss maybe later. Then this rectifier is going to convert 230 volts to 19.2 or 19 volt DC to charge the lithium battery. So 19 volts will be very common voltage in the lithium batteries, which is available in the laptop. Then this 19 voltage. If you see the display backlighting of the laptop, the top one. So when you see the display backlighting, I'll show you. This is the display backlighting. This particular block, it requires around 600 volt AC, not DC, AC. So that is taken care by the inverter. Inverter converts 19 volt to 600 volt. Some are designed for 200 also to AC form. That is given to the display backlighting. So I got an inverter here. Rectifier is there, inverter is there. Then for microprocessor and all, it may work for a 5 volt microprocessor or 2 volt microprocessor. Of late 2 volt, 1.2 volt microprocessors are available. So buck converter is a DC to DC converter which converts this 19.2 DC voltage from the lithium battery to 5 volt. That is done by the buck converter. Buck means step down the DC voltage. The chopper, other meaning is chopper circuit, DC to DC. 19 volt DC is converted to 5 volt DC or a 2 volt DC required for the microprocessor and power management in the laptop. Then If you take the disk drive may require a 24 volt DC, not AC. 24 volt DC disk drive. For that, I use a boost converter or a step-up DC to DC converter, which converts 19.2 to 24 volt DC, suitable for the disk drive. So this is my entire power management in the laptop, where we can see all the three types of the converters, which are those: AC to DC, nothing but your charging circuit, and then inverter DC to AC, the two types of the DC to DC converter: buck converter to reduce the voltage given to the microprocessor, boost converter given to the disk drive. Only one converter which is not we are using is AC to AC converter. As of now, it is not there in this entire circuit. And if you take the electrical vehicle power and drive systems, like you take a PMRCL compartments trains, it will be having everything two sets. One alternative connections will be there. And here, suppose if you see three-phase AC line 50 hertz supply, we have a battery charger here, which is going to convert it to DC voltage. DC voltage to charge the battery. Then you can see four induction motors, AC machines, or four machines are there. So two will be extra, maybe alternative processor. So this DC is converted to AC using inverter circuits and fed to the AC machine. At any instant, two machines will be running. Any two machines will be running. Remaining two will be redundant. That may be used later. Then this DC voltage, battery DC voltage, converted to the smaller DC voltages using your DC to DC converter, maybe for microprocessor or vehicle electronics or compartment door opening, closing, lighting system, AC condition, air conditioner, everything. I require some DC connection, DC value there. So this is my very basic electrical vehicle drive system. Now, so we come to know that where and all we use AC to DC, DC to DC, DC to AC. So you can imagine and you can understand by this time that power-electronic converter plays a vital role, plays a very vital role in the entire industry or the home appliances or space technology, medical electronics, whatnot. You take any field, this power-electronic converter is very important. That's why I told you most of the projects will be generated from the power-electronic converter only. And one more thing, this particular slide, I don't want to give more information, but I want to give very small information here. Now, when you want to handle more power, my x-axis is frequency. Frequency is the x-axis, 100, 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz. My y-axis is power handling capability in terms of volt ampere. So 100 MVA, up to 100 MVA. If you take HVDC system and all, it will go up to 100 MVA. If you take a electric car, the train system, it may go up to 100 kilovolt ampere, even beyond it. Car and all. If you take UPS systems, there are some limitations. If you see from left top to right bottom, if you come towards the right bottom, you can see some communication systems, some switching power supplies, and then audio systems on the right bottom, robotics, there and all. We handle very high frequency signals because our power handling capability or power requirement for those devices are very less. We take a refrigerator, certain applications, I'm not handling more power there. When you handle more power, I cannot have more frequency. That's the main important point to be taken care. When you handle more power, I cannot chop the waveform at high frequency. Very difficult. There will be more switching power losses. So when you handle less power, like if suppose you take you are charging your cell phone adapters, there they handle very high switching frequency. When they handle the switches very high frequency, the size of the magnetics is nothing but coil, the transformer, all the sizes, even capacitor size will goes down drastically. I get a compactness. I got a compact. Maybe you might have seen the laptop charges, older days and now present situations. And you see the battery charges also for the cell phone chargers. The size of the cell phone charger, previously it was the size of a brick, but now it's the size of a plug itself. A small plug size is the adapter. You can see the compactness, the flexibility, compactness, and still it can handle the power required for your cell phone. But those adapters will operate very high frequency because it's handling very less power. But when you handle more power, I cannot select high switching frequency. It will come somewhere at 50 hertz only. You can see the track, thyristor, HVDC line, very first line, vertical line. There, the frequency is 50 hertz. There I'm handling more power. What kind of switches I have to use? Definitely my thyristor family members. So we had been to Power Grid Corporation of India Limited, PGCL Kolar. So there was a power line coming from the Orissa Telchi, where 400 kV DC line is there, and they what they do, their DC is converted to AC using inverter circuits made up of the thyristor family members. So they have a huge building where only thyristor will be dumped there in that particular PGCL. That's basically grid, one of the grid in the southern side. So the HVDC, HVAC, they handle very huge power. There, I cannot handle the switch at high frequency. Very small frequency I can handle that because I'm handling more power. Okay. So simple to say that when you have a more power, I cannot select more frequency for the switching. When you have more power, less frequency. Less power, more frequency I can go for because they're inversely proportional here. Okay. So these are the highlights I would like to share with you people. If you have any doubts in the Powertronic converters, so far what I discussed, any doubts other than the syllabus or whatever I taught, you can just share with me. Then I start the experiment number 2, static characteristics of MOSFET and IGBT. I'll start now. So before that, can somebody share any doubts you have or you could able to follow otherwise? So I'll think that yes, my friend will talk, so I'll be keeping quiet. No, don't worry. Everybody can just put a word. I'll be very happy. Somebody can unmute and just put some words. Somebody can share? Yeah, who is this? I'm not able to hear, please.
No doubt, sir.
Okay, hey, okay, it's not
Aditya.
Aditya, it's not the question of doubt. You can share some interaction, you can have some questions about Powertronic converter, what you felt. It's a very vast technology, right? Now the booming technology is EV
Yes.
technology, electrical vehicle technology, renewable energy sources. It's a booming like anything as of now, because every car company has their own Powertronic converter and EV technology field. They have started their own R&D, right? Okay, okay, shall I continue? Ramesh,
Sir.
Ramesh, Ramesh is there. Aditya Ramesh, Ramesh, unmute madapa. Aditya Ramesh, Aditya Gautam.
Yes, sir.
Okay, you were there from the beginning.
Yes,
Gautam, you
sir.
are there. Okay, good, able to follow, right?
Yes, sir.
Okay, that's good. Let's continue. Let's focus on the experiment number 2, static characteristics of MOSFET and IGBT. So there are two characteristics we are going to study for the any switch. One is called static characteristics. Another one is called dynamic characteristics. Okay. When you say static characteristics, we come to know what is the threshold voltage of the switch. Threshold voltage means normally we say cut-in voltage, threshold voltage for a switch. What's the cut-in voltage, threshold voltage for a diode? Cut-in voltage say is a 0.8. If the voltage is more than 0.8, then diode start conducting. So threshold voltage means that threshold voltage till you attain threshold voltage, the switches won't conduct. If it's more than threshold voltage, more than your depletion region voltage, then the switch will start conducting. We want to know about the threshold voltage of the switch. Then the one question here, anybody can answer. When you want to buy a MOSFET in the market, what are the various parameters you want to tell to the vendor? So MOSFET has got 3 terminals. Gate is called control terminal. Drain is the power terminal. Source is a common terminal there, very common terminal. So we have two loops here. Left hand side loop, what you call It's a control loop. Let me write that. So this is my control loop. Two loops here. Control loop. The moment I give the gate signal, MOSFET will be turned on. Right hand side is a power loop. This is my power loop. Why it's called power loop? I'm handling more power here. What are the resistance I'm showing here? Rheostat. This is nothing but my load. Maybe a bulb. Maybe some appliances. So this 6 amps rheostat resembles my load. The load can be anything. It can be induction motor, it can be DC motor, it can be refrigerator, it can be anything, right? So that is my load. There are two loops are there, control loop and power loop. Using control loop, I want to turn on the MOSFET. So very simple idea is when you turn on the MOSFET, drain and source is shorted. When the drain and source is shorted, the full current will flow, a rated current will flow through the MOSFET and give power to the my load, right? And left hand side is my control loop. So when you say static Cat 6, very important parameter what I want to find is that I want to know the threshold voltage VTH of the MOSFET, as well as I want to know what is the output resistance of the MOSFET or not. These are the two important parameters I am going to get from this particular experiment. Now, whenever you want to buy the MOSFET in the market, you have to tell to the vendor three important parameters, very basic parameters. Can somebody share at least one or two parameters? You want to buy a diode, you want to buy a MOSFET. What are the various ratings you tell to the vendor to buy it from SP Road, Bangalore? Tell me boldly. If it is error, doesn't matter. No one will question you.
Current around
So
capacity.
voltage,
Voltage. Okay,
5
voltage is
volts or
one.
12 volts.
Okay, voltage. One is a current. Who's told this?
Harshal.
Pardon?
Pavitra.
Pavitra?
Harshal.
A little bit louder.
Harshal, sir.
Harshal. Okay, good. Don't worry. You tell your name and tell. See, should have more confidence in telling the answer. Both answers are correct only. So we are going to tell what you call forward blocking voltage of the MOSFET. We are going to tell the drain current requirement. We are going to tell RDS of the MOSFET. RDS is nothing but the output resistance of the MOSFET. That we are going to find this from this experiment. Why this RDS is so important is that lesser the RDS, less power losses in the MOSFET itself, because MOSFET is going to carry the drain current. So my drop across my VDS is ID into RDS. When RDS is very small, obviously the losses will be very less. That is a basically static power loss. So R0 or RDS is the static power loss. That will be very less. Because since it's very less, my power loss will be very less. My efficiency of the power electronic converter will be high. So how to improve the efficiency of power electronic converter? You choose a MOSFET whose R on or RDS is very less. For example, I tell you, if you take a IRF, International Rectifiers MOSFETs, they mention that RDS is equal to 2 ohms. 2 ohms. But defense people won't select such MOSFETs. They want RDS as less as 0.01 ohms. So they don't want to see any power loss in the MOSFET because they operate this power electronic converter in the defense as well as the space technology, right? So there it should be very meticulous. It has to handle, there will be least power because every part block of the space technology will be maybe requiring 1 watt 2 watt systems like that. There, if the losses in the MOSFET is very high, it's a waste. I don't want to lose the power in the MOSFET. They choose RDS on or R on should be very less. That's the importance of the RDS on. Then drain current. So how much drain current depending upon the rated current of the motor. Motor is 10 kilowatt, it requires 100 amps. That's my drain current. See, this is something like a reverse engineering. First, I choose the load. I understand the load parameter. Then I choose the MOSFET. Directly, I don't choose the MOSFET to design. VFB, forward blocking voltage. So can somebody tell me when the switch is turned on, what is my voltage VDS? When the switch is turned on, what is the voltage drop across the switch under ideal condition, not practical condition? I told you when the switch is turned on, VDS is shorted, DS is shorted. Then what is the voltage drop across the MOSFET, VDS?
0.
0, perfect. So it should be instantaneously, you should tell, correct. 0 volts because switch is turned on, right? It's a shorted. When the switch is turned off, what's the voltage available here across the MOSFET? It's open circuit, right? When you don't give the gate signal, gate drive when you don't give, MOSFET will be in the off state. So drain to source, it will be open. When this is open, what's the voltage available across the MOSFET? My supply voltage is 30 volt, right? What's the voltage available here across the MOSFET? Switch is open. Current is not flowing in the power loop. I'll show you one example. So you have a switch here. You have a supply here. Maybe I put some load here. Some load, some resistance R. When the switch is open, when you connect a voltmeter here, how much voltage it will show? My supply voltage is 10 volt, say an example. How much voltage it will show? I
10
connected
volts.
volt. Pardon? Louder, little bit louder.
10 volts.
Perfect. 10 volt. Because switch is open now. When the switch is open, the voltage drop of the switch is nothing but the supply voltage 10 volt. When the switch is shorted or turned on, when the switch is turned on, voltage is 0. It is shorted. Even though current is flowing, because whatever the RDS on of the MOSFET is least, maybe 0.01 ohms, very least, as good as the resistance of the wire itself. So the drop across the voltage across your switch will be 0 when the switch is conducting. These are the very essentials in the power converter. See, there are only two problems occurs here. Either the circuit is open or circuit is closed. Nothing else here. Now, this VDS, whatever I told you, what you call forward blocking voltage, nothing but the supply voltage, 30 volt will be available here when the switch is open or when you don't give the gate signal. When you don't give the gate signal, same supply is available across the switch D and S. This voltmeter is going to show you 30 volts precisely when you don't give the gate signal, right? So let us put all the points in a proper order. The first thing I told you that the static characteristics of a switch is going to give you threshold voltage 1. Another one is output resistance. Output resistance. Also, it will give you transconductance that we see later. What is that? Then that these two parameters we are going to check for both MOSFET and the IGBT. This is our circuit diagram. We understood in the circuit diagram that there are two loops. One is a control loop, another one is a power loop which carry more power. That is why my load here is rheostat. Rheostat is a load whose rating is 25 ohms, 6 amps rheostat. Since I have taken 25 ohm 6 amp rheostat, the 6 amps fuse is there and the 10 amps ammeter is there. And VDS maybe I can connect the multimeter only here to check the voltage. It won't go more than 30 volts here because supply voltage is 30 voltage. Then this is a basic understanding of the circuit. Now we need to conduct the experiment. When you want to conduct the experiment, there are two categories. The first category is called as transfer characteristics of the MOSFET. What do you mean by transfer? When you say transfer, one of the output parameter I'll take and one of the input parameter I take. So output side means we have a VDS. VDS is output voltage. If you observe here, VDS is the output voltage. ID is the output current. On the left hand side, the input voltage is VGS, input current is IG. So why we tell like this is my output power is given to the my load, that is my power loop. Input side is, we say input side because it's a controlled signal, controlled voltage that I give from the power supply 1. We have two power supplies. Power supply 1 we handle with the 15 volt, power supply 2 we handle with the 30 volt. Is a huge power. Now here how we conduct the experiment is that we want to know what is the threshold voltage or a turn on voltage of the MOSFET. Threshold voltage is that, I'll show the curve. The curve will be going to something like this. So transfer characteristics is a plot of drain current. Drain current is nothing but the output current. Drain current is nothing but the output current versus input side voltage VGS. That's why we say transmit transfer. So output to input or input to output. That's why we say transfer. So ID is the output current or I naught, and VG is the input voltage VN. It's a plot of output parameter versus input parameter. That's why it's called transfer characteristics. In this characteristic, what we do, we vary VGS x-axis and we want to note down the current. Tabulate it and plot the graph. We'll get the graph something like this, a curve. This is my threshold voltage or a cut-in voltage beyond which current is start flowing in the MOSFET. So MOSFET is conducting after threshold voltage. Before that, MOSFET won't conduct. Generally, the threshold voltage for a MOSFET IR of 840, 850 and all, it is 3.3 volt. It is no down. Threshold voltage of the MOSFET, what you get in the lab also is around 3.3 to 3.5 volt. If it is more than 3.5 volt, which my VGS is more than 3.5 volt, then only MOSFET will be turned on. Then only drain current start flowing. That's why we say it's a control terminal. Come back to the circuit. So go to the this is my control terminal. The gate is a control terminal. When VGS is more than threshold voltage, then only MOSFET conducts. Then only drain current start flowing. Now observe. My conduction of experiment like this. Power supply 1, 15 volt. Power supply 2, 30 volts. VGS, VDS are the multimeters I can put it across. And the one ammeter also multimeter I can put it there to know the collector, the drain current. One rheostat in cut-in position, I put it there. 6 amps fuse will be there in the box itself. You have a modules, all of them are modules, don't worry. You have ample of modules are there, you just have to connect it using wires. Now, after rigging up this circuit, this RGS, you can see RGS, the resistance between the gate to source, that is there in the module itself already. You would not to connect some external resistance. RGS is the resistance across gate to source to give a path for the capacitance effect of the MOSFET. MOSFET is basically a capacitor element. Now what will happen? Between the gate and source we have a capacitance. Gate to drain we have a capacitance effect. Drain to source we have a capacitance effect. We have 3 capacitances here. Between gate to source we have capacitance effect. It has to discharge. So once you don't give the supply, the discharge path is given by the RGS. So that is the element which is already there in the module. You need not to rig up the circuit. Hardly what you do, you take a block, the module, and then take 2 regulated power supply, do the connections, and 1 rheostat. Remaining your fuse, your MOSFET, RGS, everything is a part of your block itself or the module itself. Now, when you talk about the regulated power supply, we keep the current knob maximum, voltage knob minimum always. Why? Somebody can answer. I take a 30 volts 2 amps regulator in the lab. When you do conduct any experiment, you might have done in the analog circuits and electronic circuits and all. We keep current knob maximum, voltage knob minimum at time t is equal to 0. Why? Somebody can answer. Why the current knob is kept maximum, voltage knob is kept minimum initially? These are the Viva questions. We'll ask you this type of Viva questions. You should know. Okay, it is something like this. If you have a VRPS, the VRPS rating will be 30 volt 2 amps. Now my requirement is for 1 volt 2 amp I require, or a 5 volt 2 amp I require, or a 20 volt 2 amp I require, or a 30 volt 2 amp I require. Every voltage value I expect 2 amps of current to drive, to be driven by the MOSFET, to be driven by the your VRPS. So we expect that the circuit of the VRPS is ready to drive the 2 amps for any voltage. For any voltage. If you make the current knob minimum, it cannot drive the current at all. If you keep it very minimum, 0.1, if you current the moment, you current the load. If the current exceeds more than 0.1, it will give a beep signal, it will switch off the supply. So that should not happen. You ensure that RPS is kept at 2 amps, so it's capable of handling 2 amps irrespective of the voltage. We are giving path for the current to drive more from the VRPS. That is why what we do, we keep the VRPS current knob maximum, voltage knob minimum. It should handle the current as much required to drive the load there. Then Now let us conduct the experiment. How to conduct the experiment? It is something else. This very simple steps. Can we observe what are the steps? I am going to tell it here. Same thing holds good for the IGBT also. No changes. Now first step 1. So let me take the pen. Step 1. The first set PS1 0 volts here. 0 volts by operating voltage setting knob. Do not operate the current setting knob. Keep it at maximum and leave it. The switch on the PS1. Then switch on PS2. Set VDS to 30 volts here. The moment you set 30 volts, VGS is 0 here. The voltage across my switch is exactly 30 volts. Even this voltmeter will show 30 volts. Will show 30 volts because switch is open. Then the next point what it says, increase PS1 gradually. Increase that's PS1 gradually so that VGS will be gradually increasing 1 volt, 2 volt, 3 volt. Current won't flow till my VGS is equal to or greater than equal to VGS threshold, which means that when VGS is greater than or equal to VGS threshold of the MOSFET, then we expect some small current flow here, maybe some 0.01 amp. This is my first reading in the tabular column. The first reading is, the step goes like this: set PS1 0, set PS2 30 volts, such that VDS also, voltmeter also shows 30 volt here. Gradually increase PS1, 1 volt, 2 volt. Don't go very faster, very slowly you have to increase, because you have to identify the threshold voltage very, very meticulously, correctly, perfectly. So gradually increase VGS and observe your ID drain current carefully. At one particular point, it's a small current, 0.01 amps of current will flow in the drain part, which implies that whatever the voltage is shown by the voltmeter, that is my VGS threshold. That is my first reading. I can say my first reading will be something like this. I note on the first reading as VGS threshold may be 3.3 volt. At 3.3 volts, maybe some small current, 0.01 amp of current is flowing. That's my first reading. Before that, you don't take till the drain current is flowing. Then next step, what you do? You gradually increase further to 4 volt, 5 volt, up to 15 volt, and note down the drain current. Now you note down VGS and the drain current for the constant VDS. For the constant VDS, because I set my VDS constant, I am not varying that further. Only what I am doing, I am varying the PS1. Varying PS1 from 0 to towards 15 volt. Don't go more than 15, towards 15. Note down your VGS input voltage and ID drain current. So since we are noting down input voltage and output current, it's called transfer characteristics, and we want to plot it. Then repeat the above procedure by setting your VD, the PS2 is equal to 20 volt or 25 volt, doesn't matter. Set this 20 volt or 25 volt, also no problem. Set this 20 or 25 volt, one particular reading. Set this, fix this, don't touch further. Again, increase PS1 gradually from 0 towards 15 volt. Don't go more than 15 volt. At one particular point, somewhere again at 3.3 volt or 3.4 volt, nearly the drain current start flowing here. So once you can encounter some small current flow in my power loop of 0.01 amps, then you note on that that's the first reading, which you can see here. This is second. So I think no, here, yes, here VGS, here you set VGS 25 or 20 volt, doesn't matter. Threshold voltage you note down immediately when the drain current is 0.01 amps. So again you take a set of reading here also. Take the readings for VGS 25 volt up to your VGS reaches 15 volt. Reaches 15 volt here. Yes, this is my transfer characteristics. Is a plot of input voltage VGS versus output current ID for a fixed output voltage VDS. So we have taken two cases here, case 1, case 2. So you can, it's enough to write plot for only one case. So this is a plot what you are going to get there. As I told you, this is the point here afterwards. So this is the point here afterwards. My drain current start flowing. At this point, my value will be VGS is 3.3 volt and the current will be somewhere at 0.01 amps. 0.01 amps. Further, you can go up to 15 volt, somewhere here up to 15 volt. You can go up to 15 volt. Then you can see current maybe around 1 amps, 1 to 1.5 amps. You tabulate all of them, tabulate this and rate a slope. When you rate a slope, already I got VGS threshold, which is very important for me. I also calculate what you call as transconductance GM. What is conductance? Reciprocal of resistance. So what is conductance means? When you say resistance, resistance is equal to voltage by current in ohms. What is conductance? G. G is equal to I by V. This conductance, but I say it transconductance. Why it's called transconductance? Transconductance means maybe output current by input voltage. It's a transconductance. So my output current is nothing but your drain current ID. Input current is nothing but the VGS. This is my input voltage. That's why it's called transconductance, not a general conductance. Transconductance, the change of output input, something like that. Now we put a slope here. The slope parameters are, one is delta ID parallel to your y-axis. Put slope anywhere. This is my delta ID parallel to y-axis, delta VG parallel to x-axis. So note down the delta ID, delta VGS, take the ratio that we say transconductance GM. So GM is equal to change in drain current delta ID by change in the input voltage delta VG in mhos. This is the first part of the experiment is over. Then, any doubts here? Do you have any doubts? Somebody can respond.
No, sir.
Okay, voice is very feeble. Louder. Yaar ಹೇಳಿದ ಅವರು louder ಆಗಿ ಹೇಳಿ ಜೋರಾಗಿ.
No, sir.
No sir. Okay. Yeah. Let me repeat the steps once again because same thing holds good for the IGBT also. Let's start. First step, I'm not reading the whatever I printed there. I'm just telling very generalistic way. Step 1, set PS1. Let me write down the values. Set PS1 to 0 volt initially and PS2 to 30 volts. Once you set PS1 to 0 volt, VGS is also 0 volt only, no doubt about it. And set PS2 to 30 volt, VDS is also appear to be 30 volts only. So this will show, this volt will show 0 volts, this volt will show 30 volt. So control loop 0 volt, power loop 30 volt. Then vary PS1 gradually in steps of 0.1, 0.2, 0.3 volt like that. At one particular point of the VGS, the drain current start flowing. So that VGS voltage, respective voltage, we call it as VGS threshold at which my diodes, MOSFET start conducting. MOSFET start conducting. Some drain current is flowing. So typically in the labs, the available MOSFET, IR of 830 MOSFET, International Rectifiers MOSFET 830. So this particular MOSFET VGS threshold will be somewhere around 3.3 to 3.5 volt. It depends. See, if you take it same MOSFET, two MOSFETs, IR of 832 MOSFETs, no two MOSFETs will be identical. Each MOSFET will give different VGS threshold. Some fractional error will be there. The reason is nobody can dope that semiconductors at the same doping level. Very difficult even you have a sophisticated devices. So doping level might change while manufacturing. So VGS threshold need not be same for the two MOSFETs of the same company. It won't be same. Now, gradually vary PS1 at one particular point when VGS is more than equal to VGS threshold, then drain current start flowing. That is noted on the first reading. Then increase PS1 further up to 15 volt and note down your VGS versus ID for a constant VDS. That is the steps I follow. This experiment I can do in 5 minutes. Just 5 minutes. I can conduct experiment 5 minutes once you are familiar. Then tabulate it. So case 1, case 2, I may go for a setting VDS power loop voltage 30 volt. Vary your VGS from 0 to 15 volt. Note down our ID. Again, note down the threshold voltage there, no doubt. Again, once again set your VDS 2.25 volt. Again, you gradually increase VGS at one particular point. The drain current flows. You increase VGS further. Note down the ID values. Write your plot for only one case, not both the cases. When you write the plot, you'll get the plot like this. From the plot, we come to know the two important parameters. One parameter which you already know, that is nothing but the threshold, VGS threshold here, after which current start flowing. Another parameter is my transconductance GM. So I put a slope here. I want to know the GM or delta G. The GM is equal to delta ID, changing the drain current to the changing the input voltage delta VGS in mhos. Okay, so this is the two important parameter. One is VGS threshold, one is a GM. These two parameters we get from the transfer characteristics. Now we go for the output characteristics. Before going to output characteristics, somebody can tell me the steps how to conduct this experiment. What are the basic steps we follow here to conduct the experiment? Anybody? Yes, Jayant. Jayant, can you share some information here? Yes, you can unmute.
Yes.
ಹೇಳಿ ಜೋರಾಗಿ ಹೇಳು. ಫಸ್ಟ್ ಸ್ಟೆಪ್ ಒನ್ ಏನು ಮಾಡ್ತೀವಪ್ಪ ಅಲ್ಲಿ?
PS1 and 0 volt.
ನೀನು ಹೇಳ್ತಾರೆ ಬರಿತೀನಿ ಒಂದು ನಿಮಿಷ. PS1 0 ವೋಲ್ಟ್. ಓಕೆ, ನಂತರ
PS2
ಕರೆಕ್ಟ್ ಹೇಳು.
maximum
30 ವೋಲ್ಟ್ ವ್ಯಾಲ್ಯೂ ಹೇಳಿ. 30 ವೋಲ್ಟ್ ಅಲ್ವಾ?
30
30 ವೋಲ್ಟ್ ಸೆಟ್ ಮಾಡ್ತೀವಿ. ಅವಾಗ VDSS ಬರುತ್ತೆ, ಸ್ವಿಚ್ ಓಪನ್ ಅಲ್ವಾ? VDSS ಬರುತ್ತೆ,
ಅದು 30 volts.
30 ವೋಲ್ಟೇ ಬರುತ್ತೆ. ಸ್ವಿಚ್ ಓಪನ್ ಇದ್ರೆ ಸಪ್ಲೈ ವೋಲ್ಟೇಜು ವಿಲ್ ಬಿ ಅವೈಲಬಲ್ ಅಕ್ರಾಸ್ ಮೈ ಸ್ವಿಚ್ 30 ವೋಲ್ಟೇ ಬರುತ್ತೆ. ಈ VGS ಎಷ್ಟು ತೋರಿಸ್ತಾ ಇರುತ್ತೆ ಅವಾಗ? 0. ಕರೆಕ್ಟ್. ಸ್ಟೆಪ್ 1 ಸ್ಟೆಪ್ 2 ಮುಗೀತು. ನಂತರ ಏನು ಮಾಡ್ಬೇಕು? ನಂತರ ಏನು ಮಾಡ್ಬೇಕು ನಾನು? PS1 ಇನ್ಕ್ರೀಸ್ ಮಾಡಬೇಕು. When you increase the PS1, what will happen? The VGS will also increase. So when the current will flow in my power loop, when VGS is more than or equal to VGS
and ID.
ಈ ID 0.01 of current flow ಆದಾಗ ರೆಸ್ಪೆಕ್ಟಿವ್ ವೋಲ್ಟೇಜ್ ನಾವೇನಂತ ಹೇಳ್ತೀವಿ? VGS TH ಅಂದ್ರೆ ಏನು?
ಥ್ರೆಶೋಲ್ಡ್.
VGS ಥ್ರೆಶೋಲ್ಡ್ ಅಂದ್ರೆ ಈ ಮಾಸ್ಫೆಟ್ದು ಪ್ಯಾರಾಮೀಟರ್ 3.3 ವೋಲ್ಟ್ VGS ಥ್ರೆಶೋಲ್ಡ್ ಇರುತ್ತೆ ಆಲ್ರೆಡಿ. ನಮ್ಮ ವೋಲ್ಟೇಜ್ 3.3 ಗಿಂತ ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಆದರೆ ಅವಾಗ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗುತ್ತೆ. ಎಲ್ಲಿ ಫ್ಲೋ ಆಗುತ್ತೆ? ಪವರ್ ಲೂಪಲ್ಲಿ ಸಮ್ ಸ್ಮಾಲ್ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗುತ್ತೆ. ದಟ್ ರೆಸ್ಪೆಕ್ಟಿವ್ ವೋಲ್ಟೇಜ್ ವಿ ಸೇ VGS ಥ್ರೆಶೋಲ್ಡ್ ಅಲ್ವಾ? ನಂತರ ಏನು ಮಾಡಬೇಕು?
ಆಮೇಲೆ VGS ಆಮೇಲೆ ID ನ ವ್ಯಾಲ್ಯೂಸ್
ಬರ್ಕೋಬೇಕು. ಏನ್ ವೇರಿ ಮಾಡ್ತಾ ಇದ್ದೀನಿ ನಾನೀಗ ಬರ್ಕೊಳ್ಳೋಕ್ಕೆ? ಯಾವ ಸಪ್ಲೈ? PS1 ವೇರಿ ಮಾಡ್ತಾನೆ, PS2 ವೇರಿ ಮಾಡ್ತೀನಿ?
PS1
ಅಷ್ಟೇ. PS1 3.3 ವೋಲ್ಟ್ ರೀಚ್ ಆಯಿತು. ಫರ್ದರ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ತಾ ಇರಿ. 3.3 ಅಪ್ ಟು 15 ವೋಲ್ಟ್ ವರೆಗೂ ಹೋಗ್ಬೋದು ನೀವು ಅಲ್ವಾ? 15 ವೋಲ್ಟ್ ವರೆಗೂ ಹೋದಾಗ ಇನ್ಪುಟ್ ವೋಲ್ಟೇಜ್ VGS, ಔಟ್ಪುಟ್ ಕರೆಂಟ್ ID ಎರಡು ನೋಟ್ ಮಾಡ್ಕೊತೀರಾ. ದಟ್ ಈಸ್ ಮೈ ಟ್ರಾನ್ಸ್ಫರ್ ಕ್ಯಾರೆಕ್ಟರಿಸ್ಟಿಕ್ಸ್. ನಂತರ ಅದು ಪ್ಲಾಟ್ ಬರೆದು ಅದರಿಂದ ನಮಗೆ VGS ಥ್ರೆಶೋಲ್ಡ್ ಆಲ್ರೆಡಿ ಇಲ್ಲಿ ಗೊತ್ತಾಗ್ಬಿಡುತ್ತೆ ನಿಮಗೆ. ವಾಟ್ ಯು ಸೇ ಇನ್ ದ ಟೇಬಲ್ ಓನ್ಲಿ ವಿ ರೈಟ್ VGS ಥ್ರೆಶೋಲ್ಡ್ ಹಿಯರ್, ಆಲ್ರೆಡಿ ಗೊತ್ತಿರುತ್ತೆ. ಸೇಮ್ ಥಿಂಗ್ ಪ್ಲಾಟಲ್ಲೂ ಬರುತ್ತೆ. ಈ ಪ್ಲಾಟ್ ಹಾಕ್ಬಿಟ್ಟು ಒಂದು ಸ್ಲೋಪ್ ಹಾಕಿದ್ರೆ ನಮಗೇನು ಬರುತ್ತೆ ಅಂದರೆ VGS ಥ್ರೆಶೋಲ್ಡ್ ಒಂದು, ಇನ್ನೊಂದು ಟ್ರಾನ್ಸ್ಕಂಡಕ್ಟೆನ್ಸ್. ಸೊ ಟ್ರಾನ್ಸ್ಕಂಡಕ್ಟೆನ್ಸ್ ಅನ್ನೋದು ಇದು ಡೆಲ್ಟಾ ID ಬೈ ಡೆಲ್ಟಾ VGS ಅಟ್ ಕಾನ್ಸ್ಟಂಟ್ VDS ಆಫ್ 30 ವೋಲ್ಟ್. ಸೊ ಒಂದು ಪ್ಲಾಟ್ ಹಾಕ್ತಾರೆ ಸಾಕು. ಗಾಟ್ ಇಟ್?
ಎಸ್ ಸರ್.
ಓಕೆ, ನೌ ಲೆಟ್ಸ್ ಗೋ ಟು ದ ಸೆಕೆಂಡ್ ಪಾರ್ಟ್. ಸೊ ಈಗ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಅರ್ಧ ಮುಗ್ದೋಯ್ತು. ಸೇಮ್ ಥಿಂಗ್ ವಿ ಡೂ ಫಾರ್ IGBT ಆಲ್ಸೋ. ಫಾರ್ ಮೀ ಎಕ್ಸ್ಪ್ಲೇಷನ್ ಇಸ್ ವೆರಿ ಈಸಿ. ನೌ ಔಟ್ಪುಟ್ characteristics. When you say output characteristics, it's a plot of output voltage VDS versus output current ID. So output characteristics is a plot of output voltage VDS andre VDS versus output current ID for constant VGS. ಸೊ ನಮ್ದು ಎರಡು ಪ್ಯಾರಾಮೀಟರ್ ಔಟ್ಪುಟ್ ಔಟ್ಪುಟ್ ವೋಲ್ಟೇಜು ಔಟ್ಪುಟ್ ಕರೆಂಟು ನನ್ನ ಕಾನ್ಸ್ಟೆಂಟ್ ಯಾವುದಂದ್ರೆ ವಿ ಜಿ ಎಸ್ ಇಸ್ set as a constant parameter, constant k. So let us see how to conduct the experiment. Now, beginning only, we set PS to 30 volts so that VDS is also 30 volts. Then vary this PS1 such that your VGS, what you are going to set there, slightly more than the VGS threshold, whatever you got already, which means that I came to know from the previous experiment that VGS is 3.3 volt. Then go to already. You put somewhere here, somewhere around 3.8 volt or 3.9 volt. ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಆ VGS threshold ಇಂದ ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಸೆಟ್ ಮಾಡಬೇಕು. ನೀವು ಅದರ ಜಾಸ್ತಿ ಸೆಟ್ ಮಾಡಿ ಏನಾಗುತ್ತಂದ್ರೆ ಸ್ವಿಚ್ ಕಂಡಕ್ಟ್ ಆಗ್ತಿದೆ ಅಲ್ವಾ, ಸೊ ದಟ್ VDS is no more 30 volt. ಅದೇನಾಗುತ್ತೆ ಕಡಿಮೆ ಆಗ್ತಾ ಇರುತ್ತೆ. When VGS is keep on increasing, switch current ಜಾಸ್ತಿ ಫ್ಲೋ ಆಗ್ತಾ ಇರುತ್ತೆ, ಅವಾಗ ಡ್ರಾಪ್ ಕಡಿಮೆ ಆಗ್ತಾ ಇರುತ್ತೆ. VDS is also be keep reducing. When the switch is perfectly turned on, complete turn on ಆದರೆ VDS 0 ಆಗಿಬಿಡುತ್ತೆ. Even the supply voltage is 30 volt. Our 30 volt will be available across my resistor. Okay, in that way. So what we do here is that set your VGS value which is slightly more than the VGS threshold what you had last experiment. So I put 3.8 volt. So this was 30, no doubt, but VDS will go down because the switch is already conducting. VDS is no more 30 volt. It may go somewhere at 50 to 60% of the supply voltage. So 50% supply voltage 15 volt ಬಂದಿರುತ್ತೆ, or 60% of supply voltage 18 volt ಬಂದು ನಿಂತ್ಕೊಳ್ಳುತ್ತದು. ಯಾಕಂದ್ರೆ ಇಲ್ಲಿ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗ್ತಾ ಇರೋದು ಜಾಸ್ತಿ ಆಗ್ತಾ ಇದ್ರೆ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಆಬ್ವಿಯಸ್ಲಿ ನಮಗೆ ಸ್ವಿಚ್ ಇಸ್ ಕಂಡಕ್ಟಿಂಗ್, ಸ್ವಿಚ್ ಇಸ್ ಕಂಡಕ್ಟಿಂಗ್ ಆ ಡಿಪ್ಲಿಷನ್ ರೀಜನ್ ಏನಿದೆ ಅದೆಲ್ಲ ಝೀರೋ ಆಗ್ತಾ ಇರುತ್ತೆ. ಡ್ರಾಪ್ ಆಫ್ ದ ಸ್ವಿಚ್ ವಿಲ್ ಬಿ ಗೋಯಿಂಗ್ ಡೌನ್. ಇಟ್ ಇಸ್ ಗೋಯಿಂಗ್ ಟು ಬಿ ಪರ್ಫೆಕ್ಟ್ ಐಡಿಯಲ್ ಸ್ವಿಚ್. ನೀನು 3.8 ಇಂದ 4, 5, 15 ವೋಲ್ಟ್ ಅಂತ ಇಲ್ಲಿ ಹೋಗ್ಬಿಟ್ರೆ, ನೀನು 15 ವೋಲ್ಟ್ ಹೋದ್ರೆ ಇಲ್ಲಿ ವೋಲ್ಟೇಜ್ ಝೀರೋ ಆಗ್ಬಿಡುತ್ತೆ. ಯಾಕಂದ್ರೆ ಅವಾಗ ಸ್ವಿಚ್ ಪರ್ಫೆಕ್ಟ್ ಆಗಿ ಸ್ಯಾಚುರೇಷನ್ ರೀಜನ್ ಅಲ್ಲಿ ಇದೆ, ಪರ್ಫೆಕ್ಟ್ ಆಗಿ ಆನ್ ಆಗಿದೆ ಅಂತ. So normally when you talk about the MOSFET or transistor, you take BJT transistors, it has got only two applications. First application, I can use transistor as a switch in all the digital circuits as well as in the power converter. Second applications, I can use transistor as an amplifier, power amplifier, audio amplifier, video amplifier, or any amplifiers. So transistor purpose is only two. One is the amplifier, one is the switch. So when you go to saturation region or cutoff region, it will be permanently turned on or permanently turned off. When you maintain the transistor in the active region, it will be in the amplification mode. ಅವಾಗ ನಾನು ಸಿಗ್ನಲ್ ಆಂಪ್ಲಿಫೈ ಮಾಡ್ತೀನಿ. ಬಟ್ ಇಲ್ಲಿ ನಾನು ಮಾಸ್ಫೆಟ್ ಇಟ್ಕೊಂಡು ಯಾವ್ದು ಆಂಪ್ಲಿಫೈ ಮಾಡ್ತಿಲ್ಲ, ಸ್ವಿಚ್ ತರ ಬಿಹೇವ್ ಮಾಡ್ತಾ ಇದೀನಿ. ಬಿಹೇವ್ ಮಾಡಿಸ್ತಾ ಇದೀನಿ. ಇಟ್ ಮೇ ಟರ್ನ್ ಆನ್ ಪರ್ಮನೆಂಟ್ಲಿ or turn off permanently. So in that way, we are going to set the VGS a little bit more than VGS threshold such that where VDS is 50% of the PS2, it may set up to 15 or 18 volt. 18 volt ಅನ್ಕೊಳ್ಳೋಣ, ಸೆಟ್ ಆಗಿದೆ. This is my first step. First step is set your VGS more than VGS threshold such that VDS is falls to 50 to 60% of the PS2 30 volts. That's my first step up. Then I'm going to take only 3 readings here. Sorry, 6 readings. The 6 readings are after setting VGS threshold more than VGS more than VGS threshold, PS2 which was 30 before and VDS was 15 or 18 before, what you need to do? Reduce PS2 to 0. Reduce the PS2 to 0, then set PS2 to 10 volt, take one reading. 20 volt, take second reading. 30 volt, take third reading. What are the readings? VDS and ID. 3 readings I get from the PS2. Then cut out rheostat gradually at 3 different points. So whenever you have a rheostat, cut in means complete resistance is included. Cut out means complete resistance is excluded. Cut out rheostat, don't go more than 50%. Maybe 1 point here, 1 point here, 1 point here. Don't cut out completely. 3 different parts of the rheostat. You take another 3 readings here. 6 readings. My experiment is over. I tell you once again. Listen carefully. First step. Set VGS greater than VGS threshold. We came to know that VGS in the previous experiment is 3.3 volt. 3.3 volt. Little bit more than 3.3 volt. Maybe I said 3.8 volt. Such that VDS falls to 60% of the 30 volt, which is somewhere around 18 volts. It falls to 18 volts. So that is my first step. Thereafter, second step is PS2 was initially set to 30 volt. Now reduce PS2 to 0 volt. 0 volt. Freshly set PS2 to 10 volt. Take one reading of VDS and ID. Set PS2 to 20 volt. Take second reading of VDS and ID. Set VDS is equal to, PS2 is equal to 30 volt. Take the third reading of VDS and ID. Those three readings I got from the PS2 variation. 10, 20, 30. Then cut out rheostat gradually, don't go more than 50%. At 3 points, you are going to take another 3 readings, but don't cut out completely. So take another 3 readings here. 3 readings from the PS2, 3 readings from the rheostat. My experiment got over. So 6 readings I'll take it here. So I'll write the reading here. For example, I give you some rough idea here. Set VGS more than 3.3. I set VGS is 3.8 volt. Such that VDS is 60% of your supply voltage. Some current will flowing, maybe 0.02, some current will flowing, right? Then what you need to do, make your VDS 0 volts, set your VDS PS2 10 volt. When you set PS to 10 volt, you will get the fresh value of VDS. You get the fresh value of VDS. That fresh value of VDS I am going to note down at the first column. Note on the ID also, second column. Then set PS2 to 20 volt. Note down VDS ID. Set PS2 to 30 volt. Note down VDS ID. My VGS is constant. I am not going to touch on the left hand side. It's fixed always. Then cut out rheostat gradually up to 50%. Take another 3 readings. So plot it. When you plot it, you will get the curve like this, one of the curve. So you can see that VGS is 3.8 volt for this particular value. 1 minute, yeah. For this particular value, pointer. Yes, for this particular value of VGS constant value, I have taken the various value of VDS versus various values of ID. When you see that after particular point, after pinch of voltage, the point wherein my current will remain constant, it won't change further. You can see the current is almost a constant after the pinch of voltage. Pinch of voltage is a voltage at which drain current will be remaining constant after that. So you note down tablet your VDS and ID, plot it up. Maybe after your pinch of voltage, the current will be remaining constant. This is my output characteristics. Then you put a slope for this and take the ratio of delta VDS by delta ID. That will give my output resistance R naught, nothing but the drain to source resistance RDS, what is referred in your manual. So RDS is a plot of delta VD versus delta ID. So take the ratio, put this output resistance. This will be somewhere under 200 ohms to, it will go up to 500 ohms also. Don't be afraid of this, because as far as IR of 830 is concerned, when you see the IR of 830, it is a 500 volts forward blocking voltage switch, 4 amps it will handle. When you apply 500 volts and 4 amps, then only will give the correct RDS. It's the rated current. When you take a switch of 500 volt and give a very small voltage of 30 volt, you don't expect the exact IR of 830 RDS on, because we are conducting a small experiment where we want to know how to conduct the experiment, nothing else. But when you see the IR of 830 catalog sheet, they'll give you RDS on is somewhere at 2 ohms or 1 ohm, but we won't get it here. The reason is I am not giving very high voltage of 500. It's very hazardous for the student's point of view. We will give only a small voltage here. Note down, even if you get 200 to 500 volt, any voltage doesn't matter. It will be accepted. All the values are accepted here in between these two values. Okay, let me tell the procedure once again. Carefully observe. First step. The first step is that set PS1. Initially, condition will be PS1 will be 0 volt, PS2 will be 30 volt, and the rheostat will be cut-in portion. Everything is the initial conditions, which is not told here. Initial condition PS1 0, PS2 30 volt, rheostat cut-in portion, and then current knobs of both the VRPS is maximum always. That's the initial conditions. Now experiment starts. Set VGS, nothing but PS1, increasing PS1. Set VGS, little bit more than VGS threshold. I may set 3.8 volt, which is more than 3.3 volt what we got. Then what we need to do here, when you set VGS to 3.8 volt, VDS will be reduces to 60% of 30 volt. So it will be around 18 volts. That's my first step. Then all these readings I have not taken. Just I am doing some settings here. What the setting? Set your VGS more than VGS threshold such that VDS drops to 60% of 30, nothing but 18 volt. My conditions are ready. Now I'm going to conduct the experiment. How to conduct the experiment? Set your PS2 to 0 volt first. Then set to 10 volt, take one reading. 20 volt, take one reading. 30 volt, take one reading. 3 readings are over. Cut out rheostat gradually. Take 3 sets of reading, but ensure that the rheostat should not be more than 50% cut out. 6 readings I got. Tabulate it and write the plot. You get the plot the same way. For case 2, what we need to do that, set your VGS threshold little bit more than 3.8. I may put 3.95 volt for second setup. A little bit increase your PS1, little bit, slightly increase little bit so that my VGS threshold is still more than VGS threshold, but further more than the previous 3.8 volt, 3.95 volt over. Then such that my VDS falls to, again same thing, 50 to 60% of the 30 volt. Then, so what we do here, we just for the first case what we have done, is that VGS is 3.8 volt, which is more than 3.3 volt. Second case we may put, say an example, VGS is 4 volt. Then next step what we need to do, you just make your PS2 to 0 and vary the PS2 to 10, 20, 30 volt and note on the your VDS and ID reading. Then again, cut out the rheostat gradually, not more than 50%. Take another 3 readings, tabulate the 3 readings and plot it. That plot we say output curve or output characteristics of your MOSFET. From this plot, what and all we get? From this plot, we get only one parameter, what you call output resistance of the switch. So output resistance is nothing but R naught. R naught is a plot of delta VD by delta ID. That is, by writing the slope, I can get the delta VD and delta ID. You can take the slope anywhere and you can get the output resistance value for the MOSFET. So this is the experiment what we do in the lab. Now somebody can explain me how to conduct this output characteristics. Output characteristics. Somebody can explain me. Harshal, I'll help you. You just share the idea. Output characteristics. Harshal, you can unmute. Harshal. Yes, Adityayam. You can unmute. Yes, Aditya, come on.
Yes,
Proceed. Yes, please.
we have to set PS2 to 30 volts
Correct.
uh, and vary the VGS value.
Yes.
Sorry, sir. Uh,
Very
Set the
PS1.
vary PS1 such that VDS is 50 to 60% of the PS2.
Okay. And VGS will be more than?
3.3 threshold
Yes.
voltage.
Correct. VGS should be more than VGS threshold, what you call 3.3 volt value. Right. So VDS come down to 60% of 30, 18 volts. Correct. First step is correct. Next step.
Next, take the readings for some values and then reduce that PS2 to 0.
Correct. Then
Uh,
first reading is
and
10 volt.
10, 20 and 30.
Yes, first reading is 10 volt, second is 20 volt, third reading is 30 volt. And note down what and all?
VD and ID. VDS and
Yes, correct.
ID.
Output current is ID, output voltage is VDS. Note down and tabulate it. Correct. The next case,
And
what
now
we do?
rheostat, sir. With the help of rheostat, we are doing
Correct. Vary the rheostat and take another 3
from
readings.
its.
What's the important
Yes.
condition? Shall we cut out the rheostat completely?
No, sir.
If you cut out completely, what will happen? This part becomes short.
Total.
Correct. This
Okay.
part becomes short
Yes, sir.
because supply is turned on, switch is turned on completely. Then obviously this part becomes short. That will damage the MOSFET as well as the source. Both will be damaged. Correct. So never cut out the rheostat completely. Up to 50% we cut out. Correct. Good. Okay. That's good. Okay. Good. Now same transfer characteristics and the output characteristics we are going to do for the IGBT also. The circuit remains same. PS1 15 volt 500 milliamp, PS2 30 volt 5 amp, VGE. So in the IGBT there are three terminals called gate, collector, emitter. IGBT is a combination of MOSFET and BJT. Always remember IGBT is equivalent to MOSFET at the input side. That's why the terminal at the input side is gate as it of MOSFET plus BJT at the output side. That is why we have collector and emitter of the transistor at the output side. So IGBT is always a combination of MOSFET and BJT. Why they have combined? Because MOSFET has got an important, very important parameters. The input impedance of the MOSFET is very, very high, such that it draws very, very less current. So gate to collector emitter is always it works like a capacitor. Input impedance is very, very high, so that it draws very, very less current here. When the input impedance of any switch is very, very high, it draws the least current required to maintain, because a voltage element is a current element. Then there's a one advantage we are taken for IGBT. BJT, the on-state voltage drop, what you call RCE of the BJT, will be very, very less. Resistance will be very, very less. Even the voltage drop, VC saturation will be very, very less. The on-state voltage drop will be very, very less. That is why we have chosen the transistor at the output side. So IGBT is a combination of MOSFET and BJT. That is why we have a hybrid terminals. One is a gate terminal of the MOSFET, collector and emitter terminal of the BJT, because we have taken the advantage of the MOSFET as high input impedance, advantage of the BJT as nothing but the low on state voltage drops, low on state losses. We have taken those two applications into consideration. Then we could able to design the IGBT. My experiment is 100% same. Let us see. Circuit diagram for the transfer characteristics. Circuit diagram remains same, only the IGBT is changed. So we go step by step. What we do initially, let me note down the values. Initially what we do, set PS1 0, set PS2 30 volt, so that 30 volt will be available across the IGBT, what you call VCE. VCE. Now, IGBT, as far as IGBT is concerned, the threshold voltage for IGBT will be somewhere at 5 volt or 5.5 volt. For MOSFET is a 3.3, for IGBT is a 5 volt, little bit more. Then, vary PS1 gradually, such that at one particular point, that is when the gate to emitter terminal is little bit more than the threshold voltage, somewhere at 5 or 5.1 volt, if you reach, then the collector current start flowing. The collector current will be somewhere 0.01 amps. When the current is 0.01, which implies my switch is conducting. The moment switch is conducting, the respective voltage we say VGE threshold voltage, beyond which my switch is going to conduct. Note down that. Then further vary PS1 and tabulate your VGE and IC. So that is my transfer characteristics. So first what we did, we set our VGE, VC 30 volts, and gradually increase the PS1 here such that my VGE reaches little bit or lightly more than the your threshold voltage, say 5.1 or 5.2 volt. Then immediately drain current start flowing. That is my first reading. So the first reading, whatever you're going to copy here, 5.1 volt, same 5.1 volt I copy here. Both must be same, remember. Respective current is 0.1, not 1 amp. Which implies that the first reading here is same as here also, threshold voltage, both are same. Then further, You gradually increase PS1 and note down ID and VGE, the various values, IC and VGE, with the various values, and see the graph. The graph is same as that of the previous experiment. So the graph remains same. When you see the graph here, this is my VCE threshold of the IGBT. Take the ratio of delta IC by delta VGE. That's my transconductance. Current by voltage is conductance. Transconductance because output current by input voltage. Then that is my first experiment. Then you set your VCE instead of 30, you set it 25 or 20 volt. Doesn't matter. 25 or 20 volt. Again, do the same experiment again. So what we do here, set it to 25 volts, an example, 25 volt. Then gradually increase this at one particular point when VG is little bit more than 5 volts. Then some small current flows here. Note on the first reading. Further increase PS1 and note on VGE versus IC. Tabulate it for 25 volt constant value of the output of PS2. Tabulate it and then you note down all the values for the second case also. So this is my transfer characteristics. Once you are done for the MOSFET, same procedure we do for the IGBT also without any modification. Only change is the threshold voltage of IGBT is 5.1 to 5.5 also in some IGBTs. It's not exactly the same. IGBT to IGBT of same company may not be the same reading. It may somewhere at 5 to 5.5 volt is the threshold voltage. Then we go for the output characteristics. It's a plot of output voltage VC versus output current IC for the constant input voltage VGE. What we do, the very first point is same thing. Set your VGE little bit more than VGS threshold. Previously it was 5.1. I may put some 5.5, 5.6, some values such that VC drops to 60% of the 30 volt, which we have already set here. So it may comes around 18 volts. That's my first condition, initial conditions, is that set your VG more than 5.5 volts such that VC drops to 60% of 30 volt. Now initial conditions over. Now I'm going to conduct the experiment. Set your PS2 to 0, come from the beginning. PS2 10 volt, take one reading. 20 volt, take one reading. 30 volt, take one reading. Always ensure that PS2 is different from the VCE. They are not same. They are not same because of the resistance here. They are not same, right? So when you set PS2 10 volt, here VC will be some value. PS2 20 volt, VC will slightly vary. PS2 30 volt, again VC will be different. Note down your VC and IC and tabulate it. 3 readings are over. Then cut out the rheostat gradually up to 50%. Take another 3 readings. 3 readings. Totally we get 6 readings in the output characteristics. Tabulate it and plot it. When you plot it, your plot will be similar to the plot you got it in the MOSFET. So it's enough to write only one plot sufficient, maybe for a particular value of VGE. VGE, I can say maybe VGE is some 3.8 volt, sorry, here 5.2 volt, which is slightly more than the 5.1 what we got there. Then note down your VC and IC and put the slope there. I get R0, output resistance, plot of the delta VC versus delta IC. That's my output resistance. So this is how we conduct the experiment. Once MOSFET you are done, conducting experiment for IGBT will be similar, no changes here. Any doubts, my dear students? Any doubts you have? No questions here afterwards. Any doubts you have? Yes, who is there in the list? Yes, Aishwarya GP. Do you have any doubts?
No, sir.
Okay, Aishwarya M. Aishwarya M. I think she's entered as a guest, so she's unable to speak maybe. Anirudh, you can speak, I think. Do you have any doubt, Anirudh? Anirudh? Anushri?
No doubt, sir.
Okay. Okay. Then Bairegoda?
No doubt, sir.
Okay. Manjesh? I'm asking you randomly. Manjesh? Manjesh. Sahil Sinha? Do you have any doubt?
No doubt, sir.
No doubt. Okay. Okay. Vivek Subramanya? Vivek?
No doubt, sir.
Okay. Okay. That's fine. This video will be there anyway. Before coming to the lab physical classes, you can go through this video. You'll be more comfortable in conducting the experiments. But one should be very strong in the fundamentals. So I'm going to share the slide, whatever I've shown you right now. So it'll be maybe the fundamentals, whatever I discussed with you people. I think it will be very, very useful over a long run. Okay. So thank you all. I'll wind up the session. Thank you all. Have a great day. Yes. Thank you.
Okay, now let's start with the connections of MOSFET. So first we can see in the circuit diagram we have power supply PS1. Okay, this power supply PS1 I am using the regulated power supply. Okay, this is the regulated power supply what we have, same as what we had in electronics lab. This is the positive terminal and negative terminal. Okay, you can observe in the circuit. From positive it's going to gate. So I am connecting from positive to gate of MOSFET. Then from negative terminal it's going to source. So I am taking one more wire and I am connecting from negative terminal to source. Negative terminal to source of MOSFET. Now, when we come back to the circuit, from drain, the connection is going to ammeter negative. From ammeter positive, it will go to variable rheostat. So, I am connecting from drain. I am taking a wire and I am connecting from drain to negative of ammeter. This is the digital ammeter. This shows the values directly here. And from positive of ammeter, I am connecting to variable rheostat. Variable rheostat is the one what we used in machines lab as well as we used it in electronics lab. You can have a manual with you and you can look at the circuit diagram while doing the connections. You will get more clarity. Now from rheostat other terminal, the supply should go to power supply 2. Power supply 2, I am taking this as power supply 2. Power supply 2 positive it should be. Then from power supply negative, it should go to source. From power supply negative, it should go to source of MOSFET. Right. These are the connections. Okay, now let me show the connections once again. From PS1 positive, I am connecting it to gate of MOSFET. From source, I am giving it to negative of power supply PS1. From drain of MOSFET, it's going to ammeter negative. Ammeter positive, it's going to rheostat 1 terminal. Rheostat other terminal is going to positive of PS2 and negative of PS2 is coming back to source. Okay, this is how we need to give the connections. Then finally we have voltmeter. In the circuit diagram it's shown 2 voltmeters, but practically we are using only 1 voltmeter. First we will be using it as VDS. If you want to measure VDS, we will be placing it across VDS terminals. If you want to measure VGS, we will be changing or shifting it to VGS. Okay, this is all about connections of MOSFET. And when it comes to connections of IGBT, entire connections remains same. The only difference is instead of giving it to gate of MOSFET, I am giving it to gate of IGBT. You have both IGBT MOSFET in same kit. Instead of you giving gate of MOSFET, I am giving it to gate of IGBT. Same way, instead of giving it to drain of MOSFET, I am giving it to collector of IGBT. And instead of source, I am giving the connections to emitter of IGBT. Okay, remaining connections will remain same. Okay, this is about the connections of MOSFET and IGBT. Yeah, now let's see the conduction of MOSFET and IGBT characteristics. Here we are performing transfer characteristics and output characteristics. First I will explain the procedure for transfer characteristics. Before switching on the appliance, make sure the voltage knob is in 0 position. Okay, this is PS1, its voltage knob is in 0 position, current knob is in maximum position. Same way, PS2, voltage knob is in minimum position, current knob is in maximum position. And now this voltmeter, whatever I have connected across G and S terminals of MOSFET, is going to read VGS. Now, we have one more multimeter or voltmeter which is connected across drain and source of MOSFET. This reads VDS. Okay, this power supply PS1 is also referred as VGG, and this power supply is also referred as VDD. Since it is connected to drain terminal, it is VDD. Since this is connected to gate terminal, it is VGG. So you have to make a note of one thing. This is VGG. This voltmeter shows VGS. Okay, this is VDD. This voltmeter shows the reading of VDS. Always you have to take the readings from multimeter. No need of taking readings from the power supply what we have here. So let's switch on the power supply PS1 and PS2. Initially both are set to 0. Now what we need to do in case of transfer characteristics is, first we need to, according to the procedure, we need to switch on and we need to set the VDS to 30. So let's set the VDS to 30 volts. I am increasing the voltage and now the VDS value is set to 30. Now slowly I will vary the value of VGG and I will make a note at what point exactly the current in the ammeter shows greater than 0.1 amperes. Okay, shows exactly greater than or shows exactly 0.01. First we need to set VDS to 30, then slowly increase the voltage of VGG until ammeter shows 0.01. Now slowly I am increasing this voltage. I am increasing this voltage slowly. You should have an eye on ammeter. When ammeter shows 0.01, when ammeter shows 0.01, it is fluctuating between 0.01 and 0.00. So this value of voltage, whatever the ammeter it is showing, which is connected across gate and source terminals, is your threshold gate voltage. Indicates this is the minimum voltage required for the MOSFET to turn on. So this voltage you have to make a note. Then what we need to do is, we need to keep on increase VGS value and then note the readings of input parameter versus output parameter. Okay, this is the input parameter. Transfer characteristics gives the relation between input parameter and output parameter. Okay, the input parameter what we have here is VGS because it is the control voltage. MOSFET is a voltage control device. So we'll be making a note of this, as well as we'll be making a note of this ammeter, drain current. Okay, so we need to vary the voltage and we need to note the readings of VGS and current ID. Okay, slowly vary the values and take the readings of VGS and ID. Okay, this is how we are going to plot the transfer characteristics. Okay, you can vary this voltage till 10 or 12 and note down the readings in steps. Now let's see how to find the output characteristics of MOSFET. Output characteristics of MOSFET. First, let's switch on the supply. Initially you have to set VDS to maximum value, that is 30. Initially set this value to 30. Now if you observe the voltage across multimeter VDS, which is connected across VDS, voltage across multimeter which is connected across VDS is showing 29.3 volts. Okay, indicates MOSFET is in off state. So the entire supply voltage whatever we are giving to MOSFET is appearing across MOSFET itself. Okay, so this multimeter VDS shows this value. Now what we need to do here is, first we need to set VGG until the value in this voltmeter drops exactly to half of the voltage. So now what I am going to do, I am going to vary PS1, that is VGS, until this value goes to half of it, 50% of this value. When you go with this procedure, the DC Q point will be set exactly at the middle and we will get output characteristics properly. Otherwise, the Q point will settle down either in cutoff region or in saturation region. So first I am setting VDS to 30 volts and I am varying PS1. So slowly increase PS1 until the voltage across this multimeter drops to 50%. So I am varying it slowly. Very little and give a little time for it to settle. Okay, it has gone more than 50%. 50% is around 15, right? It is around 15. 50% of 30 is 15. Now the voltage across MOSFET is exactly 50% of the supply voltage, indicating the DC Q point is settled at the midpoint. Now what we need to do here is, we need to note the value of VGS at this point. We need to note the value of VGS at this point. The value of VGS when we got 50% of voltage across MOSFET is 4.28. Now we need to make this voltage, we need to make a note of this VGS, that is 4.28. Now what we have to do is, we should not disturb this gate side part. Okay, leave it as it is and reduce this VDS to 0, VDD to 0. Reduce VDD to 0. What we did in this process is, we had set the value of VGS. Okay, when we give VGS to any value like say 2 or 5 or 6, the Q point may result either in cutoff or saturation. We don't want the Q point to set in cutoff or saturation. We need it to be in active region. In order to fix it in active region, we had varied the value of VDS to 30. We have reduced the voltage across MOSFET to 50% of it. Then we are noting down the value of VGS. Now we are setting VGS to 4.28. I have reduced the VDD to 0. Now output characteristics is nothing but how the output parameters of MOSFET and output parameters, that is voltage and current across MOSFET, is going to vary as VDD varies. Okay, after this point you are not disturbing this side from gate side. I am varying VDD. For every 2 volts I am noting down what is voltage across MOSFET and what is current flowing through the MOSFET. Okay, this is what you need to note in output characteristics. First we need to set VGS, then bring back VDD to 0, then increase VDD slowly in steps of 2, then note down voltage across MOSFET from the multimeter connected across VDS and ID current which is connected in the form of digital ammeter. Now take it for 2 volts, then increase it to 4, note down the values of voltage and current, then increase it to 6, then take down the values. Like this you have to take down the values till 30. Okay, till 30. From 0 to 30 you need to vary VDD and you need to note down the values of voltage and current. When the PS2 value reaches 30, what you need to do is, you need to reduce the load resistance. Okay, we have load resistance here. Once VDD reaches 30, okay, you need to vary VDD in steps of 2, like 2. At 2, what is voltage, what is current, you need to note down. At 4, what is voltage, what is current, you need to note down. Now, what we need to do is, after reaching 30, we need to reduce this load resistance. Reduce this load resistance. Reduce this load resistance till 50%, and in between you need to take it 3 values. Okay, reduce it little, then note down the value of voltage and current, then reduce it little more, then take down the value of voltage and current. Okay, like this you need to reduce the resistance till 50%, then note down the values of voltage and current. Then you can do the plot. Okay, this is the procedure for transfer characteristics and output characteristics. I have shown you for one value for 30 volts. Transfer characteristics also I have shown for 30 volts. Output characteristics also I have shown for one value of VGS by setting the voltage across MOSFET to 50%. Now what you have to do is you need to take one more set of reading. First, transfer characteristics by setting voltage to 20. Instead of 30 you need to set it to 20. Repeat the procedure and take down the readings. For output characteristics, instead of setting it to 50%, you set it to 60 or 75% of voltage. That means set this voltage to 30, vary the VGS until the voltage across MOSFET reduces to 20, then take the then reduce VDD to 0, again increase it and take the output characteristics. Okay, like this you need to take two sets of readings for transfer characteristics as well as for output characteristics, and the entire procedure remains same for IGBT. I am not going to show it again for IGBT. You have to repeat the same procedure for IGBT. The only difference is instead of using GDS terminals you will be using GCE, the terminals of IGBT. The entire procedure remains same. Okay, this is about the conduction of static characteristics of MOSFET and IGBT.